Okay, thanks a lot. My name is Pratik Saxena. I'm a faculty member at National University of Singapore, and I'm presenting on behalf of my team there, and also my collaborator Ashish Kundu, who's at Cisco Research. Okay, so everybody knows that memory safety is a big problem, and it's been one of the most important problems in system security. And translating C code to Rust would be a dream solution, right? Why Rust? Okay, you could talk about any memory safe language, but why Rust? There are three important things that come to mind. One is that it provides full memory safety, both temporal and spatial. Second, it has low performance overhead. And third, it still provides low-level control over the allocation of objects, both the size and the lifetime, right? So it's not surprising that larger companies are now paying attention to this problem, as well as governments. Okay, so there have been a number of automatic translation systems that will take C code and try to generate safe Rust from it, okay? The issue, though, is that if you look at both of the common approaches, one is based on compiler-based translation, and the other one is based on LLMs, right? Both of them have sort of complementary strengths. So compiler-based tools largely end up producing unsafe code. A lot of the code remains in unsafe Rust, but it tends to have fairly good correctness, especially with respect to given test cases. Whereas LLM-based approaches end up being much more idiomatic. So they end up using mostly safe abstractions from Rust. But in the process of doing the translation, you end up getting a deviation from the original behavior of the program. So they're often incorrect when it's tested with test cases. So there's more detailed evaluation on this in the paper. I won't stress this too much. But the question that I'm asking is, given that this is what you have, is there any approach that gives you mostly safe and mostly correct translations? Okay. So it would be great if I had the answer for you, but I don't. I have a few insights that we were able to gather from a slightly different perspective. The idea is, why don't we ask humans to translate code, okay, C code to Rust, and observe whether they succeed in this task or not. So in particular, we ran a user study where we gave C code to users and asked them to do translations. And the interesting finding is that on the programs that we gave, while the existing automatic translation systems do not produce safe and correct code, human users actually do, okay? And so most of this paper is actually looking at these results and trying to explain what are the differences between the translations produced from automatic systems versus those produced by human beings to derive certain insights as to how this might be a feasible task in the future, okay? And as part of this process, we're also identifying some of the challenges that existing automatic translators could leverage. And try to solve the challenges that they have right now. Okay, so just a little bit about our user study. The user study is actually conducted with undergraduates who are taking the computer security course, undergraduate computer security course that I teach at NUS. They are aware of memory safety vulnerabilities through prior assignments, but they've had only brief introduction to the principles behind Rust. The study is conducted with the full IRB process of the institution being followed. I won't get into details of that. We asked for consent from all of our undergraduate students, and 33 out of 71 responded with okay. Only their data is used in the analysis. Any code that you see in the paper is not taken verbatim from their submissions. It's synthetic code abstracted from the insights that we want to present. Data is anonymized, it's aggregated, and considerations were given to start the process only after the grading was finished. So there's no undue influence. Okay, and the task actually is we give each participant in the study a C program and a bunch of test cases, and we ask them to produce a Rust code that is devoid of any unsafe Rust. That means it's completely safe Rust. And we ask the participants to make it correct under the given tests. Okay. So there are a total of 8 programs which are taken from the Linux port of the BSD core utils package. Roughly, they are 300 to 600 lines of C code. And the functionality is mostly to do with file and data processing, string manipulation, and parsing, and so on. Right? At the end of this process, we got about 31 final translations that are safe and mostly correct. 2 of them were not satisfying this criteria, but the rest of them were. And so as you can see, the task is actually accomplished in a fairly reasonable way. Right? So let's look at what makes this problem hard. Okay? So here is a little piece of code that I've abstracted from one of the benchmarks. And it's basically, I'll just explain it very quickly. There are 2 pointers here, P1 and P2, that are pointing to a string object. One of the pointers is mutable. That means it's trying to mutate the object. And the other one is a read-only pointer. Okay? And now it turns out that if you think about this program and translating it line by line, preserving all the pointers and read accesses to a program in Rust, effectively you'll get a REST program that you cannot compile. By principles, you cannot compile this. Why is that? Because Rust has an inbuilt principle called the AXM principle, which says that you can't have 2 aliases to the memory object, okay? One of which is mutable and the other one is immutable. Okay? This is fundamentally disallowed by the static rules of Rust. Okay, and so what this is saying is, this actually is a very simple way to explain why existing compiler-based translations fail, because this is exactly what they do. They start with the C program and first convert it fairly well into unsafe Rust, okay, pointer by pointer and line by line, and then they try to abstract or lift the data types for these pointers into safe Rust data types. Okay. At the bottom, I'm showing you instead of the code that wouldn't compile. Okay, I will show you code here that users submitted, and this is a really nice example. It's a short piece of code. It's using idiomatic Rust and compiles with the safety checker of the Rust compiler. Okay, what's the difference here? The main point I want you to take away is how do you generate this kind of code? The idea here is that instead of adhering to the low-level representation that's used in the C code, users are comprehending the code and abstracting away from it. They're abstracting away the low-level details while they're presenting their solution in a new abstract language like Rust. Okay? So abstraction is the key here. So let's dig a little bit deeper as to how did they get rid of this fundamental issue with the low-level translation. Okay? So in the user code, we see that this code has actually elided one of the conflicting aliases. There's a single pointer there. The second one has now gone and become a hidden variable inside the replace function, the string replace function that the developer has chosen here. Okay? There are other interesting smart specialized strategies that you can see. Here is a piece of code which takes the original object and clones it into 2 objects. The first is the original object that's read-only, whereas the second object is the one that you're writing the output into. Okay? So just by creating a clone of the original object, you're able to get rid of the read-write conflict that arises in the AXM rule of the Rust compiler. Okay? And similarly, there are other interesting strategies throughout the paper. I encourage you to take a look. Another observation is that compiler-based techniques, they are full of unsafe raw pointers, and they don't actually convert much of the C Rust APIs that are unsafe. They leave them as is. Whereas users often do the opposite. They end up picking safe Rust types and safe Rust methods to implement these. So in particular, what you are noticing is that users are semantically lifting these low-level pointers. Okay, for example, a char star in C would be elevated to at least 10 different Rust types, depending on the context. Okay? And this is something we observed in the code that was submitted for the users. Why are these abstractions really important? You see, these abstractions are zero-cost abstractions, meaning the temporal safety of the program is guaranteed statically if you use these abstractions, right? And if you remember, if you look at the whole literature on memory safety, you'll find that temporal safety tends to be a major runtime overhead in many of the mechanisms that have been proposed previously. Okay? For spatial safety, Rust will do partial static checks and sometimes dynamic checks through bounds checking via fat pointers. Okay, behind the scenes. Okay, and we also found that to deal with these unsafe C APIs, users are finding the corresponding Rust equivalent in the Rust programs, and when they can't find them, they are emulating the behavior of the C program of the C library in Rust. Okay. There are other interesting challenges to look at. C has mutable globals and Rust unions, both of which are not allowed in safe Rust. Okay. Compiler-based techniques don't actually deal with this at the moment, but users specialize to the context and are able to get past these issues. How? They'll limit the scope of globals into local variables, which the compiler can statically track then. Okay? And similarly, there are other abstractions that that are cleverly used in the design. Please take a look at how many different ideas there are in these strategies. Similarly, for unions, there is work that the users are basically using enums instead. Okay. Finally, the performance of the programs is well below 20%, so it's a good trade-off between performance and safety. And by the way, we did not ask the users to specialize for performance at all. Okay, so this is just out of the bat what we are seeing. I'll mention a few sub-challenges that we noticed. LLM-based translation tools, at least at the moment, need to decompose the program into segments which they can pass to LLM units. The decomposition strategy is not clear to anybody at this point, right? So what happens is that if you have functions that have dependencies with other functions in the program, you'll get 2 copies of them in 2 different segments. And when you translate them with an LLM, you'll get 2 different representations for the same function. It's not clear how you're going to stitch it back into the same program. And as the program becomes more complex, this is a bigger and bigger issue. Okay, so this is one of the open challenges. We also noticed that there is a correctness gap. The original C program doesn't always conform to the original Rust program, and you can check this through fuzzing. In fact, what we found is that none of the user programs are equivalent. We have programs which have known vulnerabilities. The translated code removes those vulnerabilities. So by definition, you're getting rid of some of the original unsafe behavior. That's the whole goal of this exercise anyway. But we also noticed that there are other logical and sort of behavioral errors in the encoding of these strings and so on and so forth. Yeah. So I'll leave these details out in the interest of time. And what this is telling us is we need to specify what's to be kept and what's to be thrown away in the process of translation. Okay. And so I'd like to end with this joke that we have in the lab, that is, if we were to launch a automatic translation service today, you have 2 options. You can give us your code, and we will do it in 5 business days using automated techniques. On the other hand, if you're willing to pay a little bit more, please use our premium plan, because we'll finish it in a single business days, because the authors of this work will do it for you. Thanks very much.
Thank you. It's very entertaining. I loved your talk. Do we have questions? Please come and state your name and affiliation.
Wes Hardiker, USC ISI. Thank you, and you've depressed me for the day. Because
apologies.
So I maintain a very popular C-based application with an awful lot of scary code in it. There's function pointers and a bunch of other stuff that make it extremely hard to translate. And what I want to know is, let's say I don't know Rust, which is actually not far from the truth. I've done a little bit. How long until I get to the point where I can actually just write something in C and then give it to a translator to, have it spit out good Rust because I don't know it? And what I'm taking away from your presentation is we're ages away from something like DARPA's Tractor or something like that from actually being functional. Is that a fair conclusion?
I think it's an extrapolation. Far away, I don't know. What I can tell you is that the existing translators don't give you what you want. Also remember that the answer to your question depends on the size and the complexity of the program. If you're working with 300 to 500 lines of code, or actually something like 50 to 100 lines of code, you're going to get okay. But if you're talking about 1,000, 10,000 lines of code, let's talk outside. I think we're going to be in the business for a long time. So yeah, I think there's a big challenge on scale here, more than these correctness issues and so on.
Yeah, I mean, the other thing that scared me about the presentation is, anytime you're manipulating character pointers to try and, do some special string math, of which I have done a lot of, right? Interpreting and picking out the right Rust function is possibly hard for a human, let alone being able for something automatic to do it.
See, I want to sort of leave you on a positive note. Human users did get it right, and pretty consistently. I was actually amazed at how well the students did. So it's not like it doesn't exist a solution. The question is, how do we automatically or mostly automatically get to the solution? So that's what I want to leave you with. But you're on point. There are challenges there.
I appreciate it. When they want a challenge, have them come talk to me.
Yes, awesome. Thanks.
Any short question? I will ask you one.
Please.
You showed us some examples of moderate complexity, but then you showed more complex graphs and there things get ugly. Can techniques like program modularization, compartmentalization analysis help?
Absolutely. I think one of the big challenges, as I alluded to in the talk, is this decomposition problem first, right? If you get that under control, your LLM errors would be localized to each segment. So definitely, there's a big role for both formal methods and program analysis techniques right there. And there'll be even more things outside that. Actually, there are nice papers that are not in the domain of C to Rust, but if you look at how other languages are translated, refactoring of code has been a major strategy before you go to anything like a direct translation. So there's a lot of work that can be done.
Thank the speaker again.
Thank you.